Amusement Park Data Part 2, Measuring Forces. We're going to measure forces with two different tools. The first one is what I call a pipe accelerometer because it has a small segment of pipe inside this plastic tube. And there's a piece of elastic connecting the pipe to each end of the tube. You'll be able to see that in the next picture. Here's the scale on the side of the tube. When held vertically, the top elastic is stretched. The pipe accelerometers we're going to use have two pieces of elastic, but you can just think of it as one spring. So don't get confused by the fact that there's two pieces of elastic. Just think, how would it be functioning if there was just one spring that was stretched? The pipe will be at different positions inside the tube depending on how stretched the spring or elastic is. And this kind of accelerometer may be used horizontally or vertically. Now this is the important idea here. What does the accelerometer reading tell you? It tells you the applied force of the elastic on the pipe. So if the accelerometer is at rest, horizontally, just sitting on the desk, the elastic is relaxed, or if you were going to think of a spring in there, right, the spring is not going to be stretched. So there's no applied force from the elastic or the spring on the pipe in there. So the accelerometer reading equals the applied force on the pipe, which is 0. Now what if you hold your accelerometer vertically and it's just at rest? Well, gravity is pulling down on the mass. We know that because we're on planet Earth. The elastic is now stretched and it's pulling up on the mass. Because the pipe is at rest, we know those forces are balanced. So the upward force applied by the elastic must be equal to the downward force of gravity. So the accelerometer reading equals the applied force, which equals 1 mg. And that's how we write and determine and figure out, calibrate, I guess, the scale of these accelerometers. We just set it vertically on the table and make a mark where the pipe is, because that tells us that the elastic is pulling upward with a force of 1 mg at that position. So to review, what does the accelerometer reading tell you? It tells you the applied force of the elastic on the pipe in terms of mg, which is the force of gravity on the object. So little m is going to represent the mass of that piece of pipe. If a person is moving with the accelerometer, and this is usually what happens because someone is holding it on a ride, what else does the accelerometer reading tell you? It tells you the applied force on the person also, but in terms of capital M times G, which is the force of gravity on the person. So the capital M represents the person's mass, and the small m represents the pipe's mass. But the idea is that you can just take that reading on your accelerometer, change the small m to the capital M, and it's telling you the force on the person. Let's look at an example. A passenger is in a car that is speeding up to the right. The passenger is holding the accelerometer horizontally and pointing toward the front of the car. So here's the accelerometer. You can see this is the piece of elastic that is stretched. So that means there must be a force to the right. What is the applied force on the pipe? Well, we get the reading right off of the accelerometer, so it's 1 mg, and it's to the right. What is the acceleration of the pipe? To find the acceleration, we need to use Newton's second law. So the net force in the horizontal direction equals the mass of the pipe times the horizontal acceleration. The net horizontal force is just this applied force of the elastic, which we already found above was 1 mg. The m's will cancel out, and we find that the acceleration of the piece of pipe is 1g, or 9.8 meters per second squared, and it's to the right. Now what about for the person or the passenger? Well, we can use the same scale, we just need to use the capital M for the person. So the applied force on the person is going to be 1 times capital M times g to the right. And that applied force for the person is caused by the back of the seat pushing them forward. So even in a car, when you accelerate, you feel more contact with the back of the seat. You feel the back of the seat pushing you forward. We can find the acceleration of the person by using Newton's second law, and the applied force was 1 mg. The m's cancel, and we find the acceleration is 1g to the right, so 9.8 meters per second squared. Example 2. What if the passenger is moving to the right but slowing down? If they're moving to the right but slowing down, the acceleration vector is to the left. And that means that we have to have some kind of net force to the left, opposite the motion, in order to slow the person down. So what is the applied force on the pipe? Reading it off the accelerometer, we can see that it's 2 mg. You can see this is the piece of elastic here, the left one, that is stretched. So that's telling you that the applied force is to the left. And we can find the acceleration of the pipe. So F net equals ma. The applied force is 2 mg to the left, and so the acceleration, when you cancel out the mass, the acceleration is 2g to the left. So 2 times 9.8 meters per second squared, which is 19.6 meters per second squared to the left. We can do the same thing for the person, and if you're in a car and your car is slowing down, there needs to be some force pushing back on you, and usually that is your seat belt, maybe a little friction between your legs and the seat, but mostly probably the seat belt. And the applied force then is going to be 2 mg. We can also find the acceleration of the person, which comes out to be 2g to the left. Our third example will be a passenger in a car turning a corner, and this is looking in the windshield at the passenger, okay, and this car is turning, as you're watching it, it would be turning to your left, but the direction of the acceleration is shown here. That's the center of the curve is over here. When you hold it across like this, when you're turning a corner, you're able to measure the centripetal center pointing acceleration. So what is the applied force on the pipe? Reading it from the accelerometer, we can see that it's 2 mg to the left, and that is the centripetal force on the pipe because it's the only center axis force that there is on the pipe. And then we can find the acceleration of the pipe, remembering that we're doing circular motion here. So the force is toward the center, 2 mg toward the center, equals m times the centripetal acceleration. And if we wanted to calculate the velocity or the radius, you could substitute v squared over r for this centripetal acceleration. And the direction of the acceleration is toward the center of the circle. We can do the same thing for the person in the car. The force that actually pulls you towards the center of a curve when you're in a car and you're turning is either friction with the seat belt, or even sometimes the side of the car. And we can calculate the acceleration of the person, which comes out once again to be the same as the acceleration of the pipe. Example 4. Now let's look at a vertical motion. A person rides the frog hopper, which moves vertically up and down. The passenger holds the pipe accelerometer vertically. While the ride is moving up, the pipe is in the position shown. So we have the pipe way down here at 2.5 mg, and you can see this is the piece of elastic that is stretched. So that tells us we have an upward force of the elastic of 2.5 mg. So the applied force is 2.5 mg upward, and this would be the free body diagram for the pipe. So we have the force of gravity downward, and this is the big difference you have to remember when you're working with vertical motion, is you have to consider that there are two forces, not just only the elastic, you also have to include the force of gravity. So the upward force we read off the accelerometer is 2.5 mg, and the downward force of gravity is 1 mg. So what is the net force on the pipe? It's going to be the difference between these two. So 2.5 mg minus 1 mg gives us 1.5 mg upward. Finding the acceleration of the pipe using Newton's second law. Our net force is 1.5 mg. The m's cancel, so the acceleration is 1.5 g upward. So if you're on the frog hopper and you are accelerating upward, the pipe will be down here in the bottom of your accelerometer. We can apply this to the person as well. So the applied force on the person would be 2.5 capital M times g, and the force of gravity on the person is 1 times capital M times g. The net force on the person, just the same as for the pipe, except you need to use the capital M. And the acceleration, the m's cancel out, the acceleration is the same. The pipe and the person will always have the same acceleration because they're having the same change in velocity. So as long as they are holding the pipe still relative to their body, they will have the same acceleration as the pipe, even though the forces will be different because the masses are different.